Thank you for the introduction. So I will present the work on the prediction of the occurrence of solar ejected particle events using X-rays from flares and machine learning. You can see the names of the collaborators on the slide. And at this point, I have to mention that this is a work that started about 2.5 years ago within the context of the ASPEX program led by Dr. Anastasiadis from the National Observatory of Athens. So a very bare bones outline. SAPs, I think we all know what they are here. I don't need to go over that. Brief discussion on solar flare, soft X-rays, and the ghost data that we use and what these data are, how we extract features from the ghost data, and then feed them into the neural network model that has been developed. Finally, results and conclusions, and perhaps a little bit of discussion. So SEPs, okay, just vast population, highly energized particle. They can wreak havoc on spacecrafts, on satellites, instruments, and they even pose a threat to to crewed missions. So we want to anticipate them. We want to be able to predict them as best as possible. So solar flares, which are one of the two main progenitors of SEPs, they emit soft X-rays. Well, actually, they emit photons in a very wide energy range, but we have data on soft X-rays. And we have data from soft X-rays from GO satellites and the XRS instruments that they have carried since 1976, which are more or less unchanged. And that is very important because it gives us a consistent data set, let's say, over many decades that we can exploit and we can use to derive very useful information and conclusions. Of course, thousands of flares occur each year, especially for solar active conditions, but comparatively very few SPs. So the answer we wanted to investigate and hopefully hopefully answer was, can we predict the occurrence of SPs? So a simple yes or no using just solar flare soft X-rays. And to do that, we use ghost data. So the ghost data, as probably almost everyone knows here, are given in two channels, namely the long channel and the short channel, from 0.1 to 0.8 nanometers and from 0.05 to 0.4 nanometers, which corresponds roughly to an energy range of 1.5 up to 25 kV. So this is very interesting because in the 10 to 25 kV, we have an overlap of multiple contributions. So we have hot plasma and electrons that give off X-rays. We have super hot, that is a conclusion in the latest years coming from resin spectrometers and stuff like that, which has been sort of verified, and even non-thermal contributions. So it is a very double, let's say, zoo of things happening there. And you can see on the bottom plot, which is a fluent spectrum of a solar flare, how it evolves across a large energy range. And you can see where the response functions of the GOES XRS instrument in blue and red, how they overlap in that specific energy range. So the dashed line is the nominal limit, so 25 kV, which gives, let's say, with any certainty results, but actually the response functions expand way beyond. So this is what we're working with, and our dataset consists of 18,000 flares that are not associated with SEPs and 220 flares that are associated with SEPs, and we use the NOAA Solar Flare Catalog with emphasis on the 1988 to 2013 time period. So 25 years of data, 2.5 solar cycles, so a very extensive, let's say, data set. And for each flare of these 18,220, we extract the time series from the long and short channel from the continuous data set that we have. So this is our basis. 18,000 no's, no's as in SEP will not happen, and 220 yes, or yeses, I'm not sure. Anyhow, so the first thing, of course, to do is to look into the statistics of these parameters. We can derive multiple parameters from these time series. And the important thing is that sort of quite immediately, you can see that there is a clear population distinction between yes SEP and no SEP. And of course, we know that for parameters such as the peak flux. It is very well known that SCPs are associated with flares that have generally higher peak fluxes. However, this also occurs for parameters that are not so straightforward to interpret as just that there was a big flare. For example, here in the plot, you can see in logarithmic scale the fluence ratio for the long and short channel, which is not, let's say, directly interpretable in the sense that, okay, there was a big flare, so we have a big number, shows a very clear population distinction. However, none of these parameters are good enough for a single, let's say, linear classification, either uniparametric or oligoparametric. So we cannot just draw a threshold and say, okay, above this threshold, I expect an SCP with a high probability, or below the threshold, I don't expect an SCP. So this means that we have multiple parameters that are sort of show a population distinction, but none of them on their own. And this is really a textbook case for high dimensionality machine learning classifiers. So we make the assumption that in some higher dimension, in a dimension space that is from these parameters, comprised of these parameters, we can make a distinction. So from each of the time series of the solar flares, we derive a number of, I don't know if this is in the way, a number of features, such as the peak flux, of course, ratios, logarithmic parameters, and many others. There are 24 in total, so this is indeed a high dimensionality input space, plus the cosine theta and sine theta, where theta is the heliolongitude of the solar flare. The asterisk there is for later. We will revisit this point in the conclusions. So let's take this input space and then feed it into our neural network, whose structure you can see here. It has 5 hidden layers. We use Likirelu as active Fasel function, and it actually provides 2 probabilities, one for yes SCP and one for no SCP, which can be easily, of course, collapsed to categorical yes or no. And for added, let's say, robustness and better generalization, to avoid the local minima in the error space, we use a committee structure where we use 3 networks. Each one is fed in parallel the input vector. They give their separate outputs, and then a consensus is used to derive the final classification or the final probabilities, and after that the classification. So we have our model, we have our data, we can train it and we can test it. We train with 180 set flares, so 0.8 of the total fraction of the data we have, and 3,000 no SCP flares. We make a random subdivision, and because we have a very strong class imbalance, of course, we use a weighted cross-central function, which in essence teaches, let's say, the network to pay more attention to the SCP flares, so adjust its weights and biases in a stronger way, in a more intense way, in order to account for these samples, and less so for the no SCP flares, of which we have very many. So we test with the remaining set of 40 SCP flares and 15,000 no SCP flares, and we can do that many times. So we use here 100 iterations to evaluate, let's say, the stability of our results and the range of what we get. And also we calculate the true skill score, which is just a true positive rate minus the false positive rate. The true skill score is appropriate here, unlike many other skill scores, because it is invariable to the class imbalance. So many skill scores do not behave, let's say, well, or do not give an objective evaluation of your performance, because they are affected by the actual number of samples that you have in each class. And the true skill score does not, so it is very appropriate here. So let's see some results. And here you can see for the 100 iterations, the percentage of correct predictions for the set hits. So how often we corrected, we predicted correctly that an SCP will happen. So we have an average of 89.6%, which is a very promising result. And we also have a big range of results, from 75% up to 100%, and that is non-negligible. I have 5 minutes. Okay, I will just go very fast, and I will just say that we have a very also high a very low actually false positive rate. So we predict that an SCP will not happen with an accuracy of 92%, and the TSS score is 0.819. So considering that a perfect score is 1, well, it's pretty high. So we wanted to do something better than that. We wanted to actually validate our results. So we used the Livo and Out validation method, where one SCP is set aside. We train with the remaining 219 and a random subset of 3,000 SCP flares. We train our model with that, and then we predict the SCP, the flare, which is associated with SCP that was set apart, to see what we get. And to be even more strict, we demand that this happens 10 times. So 10 times we train a model and we predict for that one SCP flare what will happen, and we demand that 10 out of 10 times we get a correct prediction in order to say that yes, we could predict this SCP correctly if it happens, let's say, tomorrow. So we do that for all 220 SCPs, flare SCPs, and we thus can derive independent, truly independent predictions for all of them. So this is the confusion matrix, and you can see the results here. So we have 191 out of 220 events were predicted correctly. So we have 86, a bit higher than 86% correct prediction. And also we have a very high prediction on when an SCP is not going to happen. So 92.3%, and respectively the true positive rates and the false positive rates. If I have a few more minutes, I would like to very quickly go over, and okay, we have submitted this work and it's currently in review. We did the same thing for flares above M2, which is a more typical, let's say, case for operational space weather forecasting. The thing is that we have very reduced data, so we have only 265 SCP flares. So this is at the limit of what I would consider, let's say, reasonable for a machine learning application such as this. But even thus, we get a hit rate of 74%. So we lose about 10 to 12% there, and we still retain a quite high prediction of no SCP flares, a correct prediction of 82%. So we lose about 10% in both classes, which is very, let's say, encouraging and a very robust result. A few conclusions. So, okay, we have a very extensive data set. To my knowledge, one of the most extensive data sets that I have seen, at least in publication. The major conclusion is that the majority, at least, of SCPs can be predicted only from solar flares, whether they will happen or not. We're not talking about their characteristics, while also, of course, achieving a low false positive rate. Since we use near real-time data, yes, this methodology can offer maximum warning time, of course, after the solar flare. And since it does not require CME detection and characteristics, which, as discussed, they are generally slow to be made available and can have larger uncertainties, and especially in the first estimations, we're not bound by this problem. And finally, this is the asterisk that I mentioned in the beginning. The results are on par without the inclusion of longitude parameters. They're a bit lower than what I have shown, but still quite high and quite, let's say, good results. And this may be counterintuitive, since heliolongitude technically gives us the dependence of the magnetic connectivity from, let's say, the West Lib, when we have events there and we have good connectivity or bad connectivity. But still, this is in agreement with other works, e.g., for example, for color in 2018, when they saw the same thing, that actually the inclusion of the heliolongitude, or at least in the way that it was included and in the way that we have included in turn, does not really affect the results and their, let's say, the levels of success. So this is from me. If I have one more minute, do I? Or,
yes, please go.
Okay, I will just very briefly go over this, which I found to be very interesting, because actually it relates to one of the works that Dr. Aminalragia showed before. So we wanted to see about the false positives and what's up with these false positives. Even though we have a very low rate, we wanted to see if some of them are at least explainable in a more physics way, and that takes us back to the previous discussion. So what we did was investigate the gauge proton time series after the flares, and what we saw was that for several of these flares that are detected as false positives, we have small but measurable rises in the proton radiation level. They're not high enough to be considered events. They're not even high enough to pose any serious threat or raise an alarm, for example, in the gauge sweepstakes. But they are there. So it may very well be that the model actually what is detecting these, let's say, so events. But since they're not considered events, we registered them as false positive. And actually, this was inspired by the work from McComas et al., where they showed that there are multiple of these small events, and we wondered, okay, what is happening here? So this is of course under investigation, and I think it's very interesting to actually have a model that may be detecting these kind of things, even though it was not really thought to. So with that, I will close, and thank you very much for your attention.
Thank you very much to you, Siyava. And yes, I see that Manolis has raised his hand, but I don't know if it is now or was this from before.
No, this is for this presentation.
Oh, great.
Thank you. Thank you, Yanni, and thank you, Siyava, for this interesting presentation. Maybe you mentioned it, but I did not catch it. Is there a paper of this analysis?
Yes, it's currently in review. It's submitted to the Journal of Space Weather and Space Climate. We're in the second round of revision, so I think that quite soon it will be published.
So this analysis is only about flares. You do not take into account CMEs, and you do not take into account heliographic locations, and nonetheless, you get a pretty decent performance, like you showed, right?
Yeah, actually the longitude is used. So here you can see the parameters that actually we do use the longitude, as I said, along with the 24 other, along with the 24 feature input from a time series, we do use. What I said was that when we do not include it, so only use this 24, we do get a performance which is a bit lower, but on par with what I showed. So it can function. We did that because, as you very well know better than me, it's not always easy or fast to actually detect on the sun where a flare has happened, and it would be much more efficient to just take the gauge X-rays, run them through the machine, and get at least the probability that it can then be fed either to other modules or be used by a human operator. So this was in the interest of operationability, if there's such a word.
Okay, so is this forecasting a binary forecasting, yes or no, or is it a probabilistic forecasting? I noticed that you use a 2x2 contingency table, so it looks like it's binary, but if it is probabilistic, then you probably use the threshold to obtain this table.
Well, it's probabilistic in the sense that what the neural networks output from the softmax, which is the output, is two probabilities, one assigned to one class and the other to the other class. So, of course, you can just collapse them by selecting the higher, and you can also do some kind of thresholding. But the thresholding is not really necessary because this is taken into account within the softmax by a bias, which automatically erases it. So the thresholding has been done for us. Of course, nobody is stopping us from doing it again, but actually the results were not really changed. So
do you have an idea on where the code settles with respect to this threshold?
Sorry, where
do you have an idea on where the code settles to obtain this threshold for the contingency table?
Where the code settles?
What is the selection of the code, that is? What is the selection of the code in terms of the probability threshold? So that
okay, so you mean what is derived within the training for the probability thresholds?
Yes.
Yes. Okay. No, I cannot answer that at this moment. It's probably easy to check. I have not gone into that. I was more interested in actually seeing how we can optimize the performance. But yes, of course, this is a very interesting thing, and I will be sure to look at it.
Okay. Thank you.
Thank you.
Thank you, Manoli. And I think Lenny has a question.
Yes, please. Siava, I would like to ask, how did you split your data? If you please could go back to the slide where you...
For the evaluation, you mean?
For the train and test evaluation, yes.
Okay.
Is this correct? So you use 180 flares positive and along with 3,000 negative flares?
Yes. The thing is that, as you also discussed, and the problem is in this case we have a severe class imbalance. So there are a number of ways to address this. What we found to be the best way to address this is actually this weighted cross entropy error function, where the weights are derived from the actual numbers from how many samples we have for each imbalance. So this, as I said, places more emphasis on samples that are associated with SCPs and less so in OCPs. And that is why we have also limited in 3,000 the number of no-SCP flares, because going beyond that, we found that there's actually not much difference. And as long as we have a good representative sample for training, because actually as you increase the number of samples from no-SCP flares, you just, they matter less and less and less and less. So you have an asymptote there, and it doesn't really matter if you go beyond that. So we maintained this number, and we had more flares to no-SCP flares to test with. So this is but of course, this is just for the evaluation. For the validation, we train with 219 out of the 220 and 3,000, because it's a Livo and Out validation. So we leave only one out. I don't know if that answers the question.
So the class ratio that you used was an output of the weighting function, let's say.
No, the weighting function was defined by the class ratio. It's the other way around, but yeah, along those lines.
By the optimal class ratio that gave you the best results, you mean?
Well, actually, if you want to discuss about validation, there is no optimal class ratio, because in the Livo and Out validation, which I consider the reference, let's say, results here, we use all SCPs but one, as I said, and the number of 3,000 is limited by what I said before, that going beyond that, there is no point in, you don't get any better results. So the class ratio is defined by the data in the beginning, how much SCPs, how many SCPs we had, and how many flares. So we don't make any selection, let's say, ourselves. We just follow what we have and was available.
Yes, but you have a very, very different distribution in the train validation and the test set in the previous slide. I mean,
You mean here?
the ratios are very dissimilar. I mean,
if I may interrupt you, it's a very, very interesting discussion, and
we can continue.
Please continue. Also because I've